Wonderful, and welcome Christy Sheehy to your talk. We are going to hear from you fixational eye movement as biomarker for neurological health. You represent C.Light Technologies. You're based in California, so thank you for your early participation here, and the stage is yours.
Awesome. Thank you so much for your introduction. Let me share screen. All right, can you see my screen? Wonderful. Well, thank you all so much for inviting me here today. Today I'll be talking to you about some of the eye tracking that we've done for neurological health screening at C.Light Technologies. And so with that, I'll start off by mentioning that mostly everyone that's listening in probably knows someone who's gone through a neurological disease. They impact about 1/6 of the world's population. And even though so many people are impacted globally, we still have minimal to no viable therapeutics in this space. And this problem really stems from the fact that therapeutic developers just don't have viable biomarkers that they can use to effectively stratify patients or even monitor disease progression on a fine scale. So many times what ends up happening is they need to repurpose diagnostic tools and try to use them for disease monitoring and therapeutic efficacy. So these will be subjective bedside exams, lengthy cognitive assessments, of which there are dozens. So depending on which one you use, you may have a different answer. And then finally, very expensive MRIs. And while MRI has definitely shown great promise for a lot of diagnostic purposes in neurological disease, they've actually shown quite limited correlation with early detection or even granular disease progression mapping. And in the particular use case of the neurodegenerative disease multiple sclerosis, on average, it can take 2 years to actually see a meaningful change as it would manifest with new lesions in the brain. And so even with all of these in existence, we still face minimal to no viable therapeutics for our loved ones. So C.Light's approach is a patented hardware-software combo, and it involves the most non-invasive way to assess the brain, and that's by going through the eye. And so we start our test off very much like you would at an eye doctor. So this image over here on the left, you simply put your chin onto a chin rest and then you stare straight ahead as stable as you can. We then record the very back layer of your eye, the retina, which is also the front of your brain. So the video that you see here in the second panel is actually a video of my eye, and I'm trying to keep it as stable as possible. So you'll notice some of these very small or subtle movements that are occurring over the 10 seconds of recording. And so with these high resolution retinal structure videos, we use this cellular structure to extract eye movement on the micron scale. So some of these movements are actually as small as about on the order of 1/100th the size of a human hair. So really, really fine movements that we're extracting. And so we extract the movement up to 1,000 times per second. And then we feed that time series data into our advanced analytics. And so in our particular case, we are using feature-based neural nets that can help us to delineate different visual signatures that are indicative of disease progression. But in the future, we hope as we expand onto other neurological diseases that we can also delineate between different diseases or increase our specificity. So this 89% accuracy number that you see here is actually saying if I record eye motion and feed it into my algorithms, on the other side, I can assess multiple sclerosis disability with 89% accuracy. So I'll get a little bit more into this particular number in a couple slides, but really here we're using the power of the eye and the movements that it makes to be a biomarker for neurodegenerative health. So here's an example of our device. We're actually going to be submitting for 510(k) approval for the FDA for an eye tracker, and hopefully this will be on the market by this spring to help to visualize eye motion. So what you see here is a tabletop unit where we have all of our scanning optics in the head unit, the computer is in the base unit, and then the monitor here is seen to help view the images as they are recorded. So the advantages to this type of approach are numerous. One, it's super fast. Each scan is only 10 seconds. On top of that, it's also very repeatable. So we've done a repeatability and reproducibility study where we found under a 5% variance for both frequency and amplitude measurements. So the device itself is able to do repeated measurements reliably. And then lastly, when people think about eye trackers, almost everybody will immediately go to goggles or maybe their cell phone or even the computer camera. By going to the retina, we're able to assess basically a 120x increase in information that normally would be processed by just using the outside of the eye or the pupil to track movement. And so that 120x increase basically gives us the capability to see eye movement that was otherwise invisible before. And so just for reference today on your computer webcam, we're about 1,000 times more sensitive. So in order to start using eye motion and doing research into how to use it as a biomarker, we've partnered with top-tier university collaborations. So our first study was with multiple sclerosis with the University of California, San Francisco, looking at over 200 diagnosed patients there and 100 controls. We've also opened and expanded our studies there to Alzheimer's disease, particularly focusing on mild cognitive impairment. And then we've also done a concussion recovery study at the University of Pittsburgh. So this was looking at the safe return back to sports and military following a concussion. So I'm going to start off today just talking a little bit with you about our multiple sclerosis study and then transitioning into a little bit of our early Alzheimer's work as well. So some things that are new to some individuals is that neurodegenerative diseases can actually provide eye motion abnormalities. So for the particular case of multiple sclerosis, this is no different. So I wanted to show just a couple examples of some patternistic changes that we see. So over here in the video on the left, this is a video of an individual trying to keep their eye as stable as possible. And so you'll see this video kind of bouncing around back and forth. And even though the video looks quite obvious in the movements that we see, they're actually only on the scale of about 100 microns. So again, on the scale of a human hair. So when you look over here at the size or the extent of the movements that are bouncing back and forth in these red dots, you can see almost all of them are under 0.4 degrees or under that roughly 100 micron level. And so other machines basically wouldn't be able to pick up on this. And so when you look at it from a time series perspective, the red here is horizontal movement, the blue is vertical. You can see the eye bouncing back and forth, left, right, left, right. And so some of these patternistic changes we can see and detect when nothing else can be detected in clinic. And so this helps to guide potential therapeutics in the future by seeing some of these subclinical changes. Now, this particular change was noticeable to the 52-year-old female. Some changes that we can detect are not. So this is an individual who has what we call an upbeat nystagmus. It means their eye drifts down and they snap their eye back for correction. So you can see almost all of their movements are in this upper left-hand quadrant. Each little red circle here represents one of those jerk-like movements, which we call microsaccades. So these jerk-like movements you can see here are super, super subtle on the order, again, of less than 100 microns. And so when we then take that time series data and feed it into our algorithms, it can allow us to learn more about the level of progression that that patient is currently experiencing for disability. So I'm showing you these patternistic changes to be able to motivate your thinking as I talk to you a little bit about our machine learning algorithms. So what we're ultimately looking to do is take those eye movement videos, the changes that we see in MS, and use them to predict disability for the future. So the current gold standard test for multiple sclerosis is a bedside exam. It takes 30 minutes, and it's a scale from 0 to 10. 0 means I have MS, but I could run a marathon. 10 is death by MS. So our data spans from 0 to 8. And the 92% accuracy of that bedside disability score is the current gold standard. So we want to take this 30-minute bedside exam and make it 5 minutes or less with objective information. So we've done it in two ways. I'll start on the bottom here. If we pair eye motion with two other clinical tests, one of them being how fast you walk, the other being your fatigue, we're about 89% accurate in our ability to assess a level of disability. Now, using just eye motion alone, we're already 82% accurate. And this is just the beginning. So on the right here, I show what's typical for a machine learning algorithm. Basically, as you add more patients, which you see on the x-axis here, you can increase your accuracy. So we're looking at just over 250 patients to be able to hit that current gold standard of care, which used to be a bedside exam. Now, outside of multiple sclerosis, we're also doing work and starting off in the mild cognitive impairment group, which is the earliest clinical stage of Alzheimer's disease. So some of our baseline data that I wanted to share with you today as well focuses on healthy aging. So in order to understand what's going to happen in a neurodegenerative disease, I need to also understand what is the typical aging process for eye motion. So for the healthy controls, we split them into two groups. You're 50 or under, or you're older than 50 years old. And so what I show here is two basic things. Those quick jerk-like movements that I had showed you in those videos, that's what we're mapping here. And those are called microsaccades. So ultimately, as you get older, those jerk-like movements will increase their velocity, increase their amplitude. That's the gist of these graphs here. So here on the left with peak velocity, purple is the over 50 group, pink is the under 50 group. So you'll see that these are larger velocity numbers driven by both horizontal and vertical movements. Now for amplitude, how large a movement is, this is entirely driven by horizontal movement. So for the over 50 group, they had much larger horizontal spread of movements, and that's what drove the overall magnitude. Now, lastly here, we also can look at acceleration. So again, purple here is over 50, pink is the under 50 group. And you'll see once again that both the horizontal and vertical components are different in the aging group, which make the overall magnitude of acceleration statistically different from the younger population. So why am I showing you this? Well, in order for us to really build these algorithms, we need to understand what the healthy aging brain is already doing. And that will help us to understand what differentiates neurodegeneration, particularly for individuals that are less than 50 and might suffer neurological diseases. We can then begin to see whether or not this mimics neurodegeneration, or healthy aging mimics neurodegeneration on a faster scale. So what I see as people get older naturally is that occurring at a rapid scale for younger people who are diseased. So these are some of the exciting works that we've been doing. Again, we've partnered with University of California, San Francisco and the University of Pittsburgh, but I list here other future collaborators and individuals that are excited to use our device. And then of course, I want to always end my presentation thanking the team here at C.Light Technologies. We are a small team from a startup. There's only 5 of us here, just 6 actually as of this week. And so I just want to give a shout out and thanks to my engineering team, the neuroscience, data science, and business team that I have here. And so with that, I'd like to thank everyone for your attention, and I open it up for any questions.
Thank you, Christy, so much. Incredibly fascinating technology. Let me ask you just a quick question before we hop over to the general panel discussion. You showed us retinal scans. Are you able to pick up on pathology as well, particularly like in Alzheimer's disease? There are certain people who also measure amyloid deposits in the retina. That's one. And then somewhat related to that, also on your MS example, can you pick up these changes in a patient that has active bouts, or is that always there? And is there a difference between the two stages?
Yeah, so the first question for the pathology. So we really are focusing in on functional changes, which are changes of the actual movement of the eye. That being said, we do have a high resolution picture of the retina. So we're looking at about a 5-degree field of view image of the retina. A lot of the groups that are looking at amyloid plaques are looking at usually 30 degrees or more, a big fundus image, which can show different plaque deposits. You have a certain type of fluorescence or staining that's happening. Technically speaking, we could do the same. We could do fluorescence imaging or some other type of imaging to start to look at amyloid deposits, but we want to focus our efforts really on the functional changes, as we think that some of these changes that are happening at the micron level, super small changes, we suspect or we hope that they're happening prior to this large accumulation of plaques. So that's the hope for our functional measures. In terms of MS, the question that you had asked about whether or not we can assess an active relapse versus somewhat more of a stationary disease, those are definitely questions that we're continuing to answer. So typically during a relapse, you have a larger disability score. And so our eye motion algorithms are able to detect these larger changes in disability scoring. But all of our study was cross-sectional, so a single time point. So we're now taking that data and looking longitudinally at individuals to see if we can really begin to map more of those overarching, or even predict, we hope, those overarching changes as the disease progresses.
Fantastic. Thank you so much. I'll see you in a second in the plenary session.
Sounds great.
Thank you.
Thank you.